This is Pre-Calc section 6.3, Solutions of Linear Systems by Row Transformations. We're going to be using something called a matrix, which is a rectangular array of numbers. Each number in the array is called an element or an entry. We can use matrices to solve a system of equations by using something called an augmented matrix. Here's a system. We did that in the last section. And we want to transfer it into this augmented matrix. And all you do is take the coefficients and write them in order with the constant column here by itself. So 1, 3, 2, 1 is what my first row is. 2, 1, negative 1, 2 is my second row. And there's the third row right there. And these are called rows, and these are called columns. And this is your X column, your Y column, your Z column, and your constant column. Now this whole idea of using just the coefficients is like we did in synthetic division, where we just use the coefficients to perform the division. So that's just setting up from your system into what's called the augmented matrix. Matrix row transformations. For any augmented matrix of a system of linear equations, the following row transformations will result in the matrix of an equivalent system. So if I take this system of two equations, two variables like we did back in 6.1, and put it into its augmented matrix, this is what I get. Number 1 says any two rows may be interchanged. We could have written this system back in 6.1 this way. 5x minus 6y equals 1, and 2x plus 3y equals 9. Switching the rows did not change my system any, it would not change my solution any. So the same thing holds true for this augmented matrix. I can take all of row 2 and put it in row 1. And I can take all of row 1 and put it in row 2. There will be times when we are solving these augmented matrices that we're going to want to switch rows. What we just did there symbolically is we took row 1 and we interchanged it with row 2. Row 1 went to row 2 went to row 1. Now, number 2 says the elements of any row may be multiplied by a non-zero real number. Didn't we do that back with this system? If I wanted to solve this system, didn't we multiply this through by -2 so that we could cancel those? Well, it's the same idea with this augmented matrix. I may want to multiply this whole row through by -2, and it becomes -2, -6, -16, and I'm not doing anything to the bottom row. Symbolically, what we just did is we did -2 times row 1, and we put it in row 1. One says any row may be changed by adding to its elements a multiple of the corresponding elements of another row. So here's my system, here's my augmented matrix, and let's say for some reason I want to multiply 2 times row 1 and add it to row 2 and put it in row 2. That means I will double every entry in the first row and add it to my second row. So 2 times 3 is 6, plus 5 is 11. 2 times 2 is 4, minus 3 is 1. 2 times 5 is 10, minus 4 is 6. And I'm putting it in row 2. I'm not making any change to row 1, so it's staying 3, 2, 5. Some matrices where you're asked to do a couple of these easy arithmetic steps. This says take half of row 1. Half of row 1 means divide all of row 1 by 2. This becomes 1, 2. The bottom row remains unchanged. This next one asks me to double row 1 and add it to row 2. And I'm going to put that in row 2. It's pretty standard when you do one of these multiple steps that you're going to put it in the row that you added to. So this is going to go in row 2. You might want to help keep things straight, because whatever you do is going to go into row 2. That means row 1 remains unchanged. Go ahead and get that filled in. It also means row 3 will stay unchanged. That shows that you only have one place to put this arithmetic. So we're doing 2 times row 1, so you might want to put a 2 out here, plus row 2. And just for right now, you might want to scribble this out because we don't need it. So doing this arithmetic, 2 times 1 is 2, plus -2 is 0. 2 times 5 is 10, plus 3 is 13. 2 times 6 is 12, minus 1 is 11. Another option for this, if you can't do this arithmetic in your head, is to write this down on scrap paper. Actually do 2 times this and get 2, 10, 12, and put the negative 2, 3, negative 1 underneath it. Draw a line like old-fashioned arithmetic, 0, 13, 11. Whatever works to get this matrix correct. This one says 4 times row 3 plus row 1. I'm going to put it in row 1. And because I'm going to put it in row 1, that means I'm going to go ahead and fill in row 2 and row 3 to stay as they are. So row 2 is 7, 4, 3. Row 3 is negative 1, 1, 0. And then I will do this arithmetic. 4 times row 3, so I'm going to put my 4 outside here and add it to row 1, so I could scribble this out because I want to get it out of my eyesight, and multiply by 4. 4 times negative 1 is negative 4, plus 4 is 0. 4 times 1 is 4, plus 10 is 14. 4 times 0 is 0, plus negative 8 is negative 8. You could actually do your scrap work by multiplying by the 4, writing it down, write row 1 underneath it, draw your line, add these up, and there's your 0, 14, negative 8. But the more you do of these, the better you will get with doing the arithmetic in your head. There's something called row echelon method. Matrix transformations are used to transform the augmented matrix into one that is in what's called echelon form or triangular form. The echelon form of an augmented matrix has ones down the main diagonal. We're ignoring the constant column for right now. It has ones down the main diagonal from upper left to lower right, and zeros below in this little triangular format. That's why, besides being called echelon form, it is called triangular form. This is the example of a matrix that has already been put in row echelon form. There's our ones in the main diagonal. There's our zeros in the triangle here. Once the system of linear equations gets to this point, you can use back substitution to solve the system. Now, what does that mean? Remember, this is your x, y, z column. We don't have anything in this row except a 1z equals 4, which just really means z equals 4. We know that the z value for this system is 4. This second row, we have a y and we have a z. So this is 1y plus 2z equals 9. We can use this fact that z is 4, plug that in here to find y. So y plus 2 times 4, that's 8. Subtract 8 from both sides, and y is 1. Go to your top row. We have coefficients in every column, so this is x plus 5y plus 3z equals 7. Stuff in what we know. We don't know x. We know y is 1, so 5 times 1 is 5. We know z is 4. 3 times 4 is 12. So this is x plus 17 equals 7, or x equals negative 10. So far, we've just done little bitty pieces of the whole process. So we're going to use our row transformations to get our matrix into row echelon form and thus be able to solve the equation. So number 1 says you start by obtaining a 1 is the first entry in the first column, and then transform all entries below it to a 0, meaning step by step here, I need a 1 right there. I've got to have a 1 in that position. Sometimes the way the problem is written, you already have a 1 there. Sometimes all you have to do is switch rows to get a 1 in that position. Do you see that you have a 1 right here? So I could take row 2 and interchange it with row 1. I could also do row 3 interchange with row 1. It doesn't matter. I just chose row 2. So this is now 1, 1, 2, negative 1. And then this becomes 2, negative 1, 2, 0. Row 3 remains unchanged. So that was pretty simple to get our 1 in that position. The next thing we need is to create zeros underneath here. You've got to be very systematic about what you do and in what order. So we got our 1 where we wanted it. We have to create zeros right here. We already have our 1 where we want it. So I automatically write this row as is. 1, 1, 2, negative 1. I need to create zeros. I need that right there to be a 0. And I'm going to do my row transformation of this. I'm going to multiply row 1 by -2 and add it to row 2. That is -2 times row 1 and add it to row 2 and put it in row 2. I'm actually going to do two things at once, so let me just get this filled in before I talk about the bottom row. So -2 times the top row, add it to this right here. So -2 times 1 is -2, plus 2 is 0. Now I have to do this arithmetic for the whole row. Don't go, oh great, I got my 0, I'm done. You have to do the whole row. So -2 times 1 is -2, plus -1 makes -3. -2 times 2 is -4, plus 2 makes -2. -2 times -1 is 2, plus 0 makes 2. I can do the same process and fill in this row by looking now at the fact that I need this 1 to go away and become a 0. And the way I can make that happen is going to be to multiply row 1 by -1. So this is going to be -1 times row 1 plus row 3 and put it in row 3. So -1 times 1 is -1 plus 1 is 0. -1 times 1 is -1 plus 3 is 2. -1 times 2 is -2 plus -6 makes -8. And -1 times -1 is 1 plus 7 is 8. Now we need a 1 in that position. And I notice this third row, even though it's not the right position, I know it would be very easy to get a 1 in that position right there by dividing that whole row by 2 and write it as 0, 1, -4, 4. And I'm just going to leave everything else unchanged. I try to just do one thing at a time so you don't get lost. And you're saying, why would you do that? Well, what I need is a 1 in this position, and I know I'm allowed to interchange these rows. So if I take row 2 and row 3 and interchange them, I will have a 1 where I want it. This row will now be 1, or 0, 1, -4, 4, and this will be 0, -3, -2, 2. I've done nothing to the top row. It stays 1, 1, 2, -1. So now I have the 1 where I want it. All I need to do now is get a 0 right here. Easy to get a 0 right there by multiplying this row by 3, because 3 times 1 is 3, plus -3 gives me 0. So what is that symbolically? That is 3 times row 2, add it to row 3, and put it in row 3. So that is 3 times 0 is 0, plus 0 is 0. 3 times 1 is 3, plus -3 is 0. 3 times -4 is -12, plus -2 is -14. 3 times 4 is 12, plus 2 is a positive 14. These other two rows are going to stay as is. 1, 1, 2, -1, 0, 1, -4, 4. Now this just needs one more step to get a 1 in this last position right here. If I divide this row by -14, I will have 0, 0, 1, -1. The rest of it stays the same. 0, 1, -4, 4, 1, 1, 2, -1. This is row echelon form because there's my 1s down the main diagonal, and here are my 0s in that triangular format. What I have to do now is do my back substitution. Had to come to a blank page so I could finish this out. This right here stands for 1z equals -1. That is my solution for z. This second row tells me y minus 4z equals 4. Z is -1, plug that in for z. -4 times -1 is positive 4. Y plus 4 equals 4, so y is 0. Write your equation for the top row, which is x plus y plus 2z equals negative 1. I don't know x. Y is 0. Z is negative 1. 2 times negative 1 is negative 2 equals negative 1. So this is x minus 2 equals negative 1. Add 2 to both sides, and x is 1. So my ordered triple, which is the solution to this system, is 1, 0, negative 1. I will do another example of this on the next video. I just can't fit it all in on this one.